Okay, welcome back, everyone. So we have lots of things to cover this week. So let's get to it. All right. So if you remember last time we were talking about branch predictors, and we start talking about the importance of the branch predictors and different ways of doing branch prediction. We start talking about BTBs and RAS and BHTs, and then we start talking about kind of optimizing the branch predictor, and said that one big thing that many people do is looking at the global history as well. We use this register called global history register, and then the question becomes that how do we kind of combine the global history with what we call a local history? Any question?
On the next slide.
What's that?
The next slide, I have a question.
Oh, this one?
Yeah.
Yeah. So the way we do it is we are XORing the program counter, which is the representative of the local history, with the global history, which is kind of like giving us some notion of the recent trend in the branch. And then when we are XORing together, then we will have an index to a table, and that table kind of remembers things. And then we can have a bunch of these tables if you want to. We can have a two-way indexing of these, something like this, actually, that not only you have just 1D table, you can have 2D tables of kind of like, based on different kind of like combination of these, you can access these different tables. Yeah.
So back to the G-share predictor.
Mm-hmm.
I understand that you get the XOR and you get like an index into the table.
Uh-huh.
Where does the prediction come from? Is it specifically that index of the table, or is it like an XOR of all?
No, that particular one. So each one is a 2-bit number. Like it's this, each one is this, like each row of this table is just a regular 2-bit hysteresis counter that has 1 1 1 0 0 1 0 0. The same thing that we discussed last time.
So it's just a bunch of state machines.
But yeah, it's a 4-bit. Yeah. And then the left bit is essentially gives you the prediction. So if it's 1, it's taken. If it's 0, it's not taken. And this hysteresis bit, you only update it when the branch is actually known. So once the branch is taken or not taken, you go back to the same thing. You update your global history. You also update your hysteresis bit, basically. Yeah.
What is the difference between G-share and Taj? Because I was looking through the risk boom architecture stuff this morning, and it looked like it had Taj.
Yeah, we're gonna get to it. I think it's pronounced take, but yeah, we will get to it. This is actually the second thing we're gonna talk.
Okay.
It has both, actually. Boom has both of them. Has both G-share and take.
Okay.
Yeah.
Is there some more effective functions to replace the XOR?
Good question. Is the better effective? No. Well, I mean, XOR gives you enough kind of distribution between the bits that's kind of like people use it. Also, keep in mind it's very fast. But yeah, you can use any hashing algorithm that takes 2 and produce 1 index. You can use, so you can actually use more sophisticated hash. You can use different types of XORing. All of them could be possible, but state of our use, like a modern system usually use XOR. It gives you enough, and it's a good balance between performance and simplicity. Yeah.
So here we have a PC of 4 bits and a global history of 4 previous decisions.
Yeah, this is just an example of 4-4. Yeah.
So will you necessarily have to have your global history PC be XORed in such a way that you have the same number of counter tables? If so,
yeah,
that builds rapidly, right?
So PC, I mean, XOR is a bitwise operation, so of course you cannot like XOR larger things with smaller things, and the outcome of the XOR should be the number of rows that you have. So the bigger the rows, the more bits. But both global history and PC could be much more. Like PC usually is 32-bit number, right? Yeah. So you pick like 4-bit of it, or you just do 1 round of mapping between like a large to mid-size and then to a lower side, and then do this. So there's, again, back to that question, the PC generation could be also hashed. So you take the PC and you hash it. Actually, if you actually look at this, you will see that what we do is kind of we generate some form of a hash in order to read this table here, and it gets the entire PC bit, but then this hash kind of reduce it to the size that we want for this particular counter table. Make sense? Any questions from? So this is actually the early implementation of Gshare in Boom Core. And again, my suggestion is if you want to see the details, you can always go to the code base and look at the Gshare prediction function and read that. That's usually very helpful. So there are many optimization for Gshare. One example I'm showing you here is called G-skewed predictor. So essentially, the idea here is that you can have a global and a local, and then what you can do is then you can have multiple hashing functions. Instead of just having one XOR function, you can have multiple of these hash functions, okay? And then pick the corresponding table. So instead of having like one column, you can have many columns depending on how many times you have this different hash generation. And then each one will give you a separate index, right? So depending on how you hash it, one can, for example, select this one, the other one can select this one, the other one select this one. Then you get different decisions from these different tables, right? So for example, let's say this one gets, say, taken, this one says not taken, this one says taken. And then here you can do different things. You can do majority, for example, see like, which one is the most, and then maybe if you pick odd number, you will always guarantee that there's a majority. Another thing that you can do is you can do some form of dynamic decision making, as in, for example, you can measure how accurate each of these columns are, right? I can measure the accuracy of each one. And if I see that, for example, oh, this one is consistently better than the others, maybe I give more weight to this column. And I can dynamically even change that, right? So there are a whole bunch of dynamic decisions one can make in order to make this event better and better. And there are all of these things have been implemented a lot in real systems. But the general idea is, how do we really index, how many tables do we use, and how do we index them? Like generally, how do we hash into this? And you can actually use them. Well, actually, this could be a good idea for your project as well, for your implementation, to consider having multiple of these tables and then using different hashing algorithms and see which one really performing better. Okay. So now that we talk about this, let's actually talk about a more advanced one, which is also like commonly used in systems, and that is what we call a take processor, take predictor. So as you remember in Boom, we have a predictor which we call the backing predictor. That's more complex. It takes more cycles. The reason for this is like it checks more history and different things at the same time. And that's why it's kind of like the trade-off between having a better branch predictor, but having the longer kind of pipeline. And this is again what we showed so far, that you can have a BTB. BTB essentially just take 2 cycles, but this more sophisticated branch predictor kind of takes 4 cycles for us to do it. So what is that branch predictor? That's the one that you said as well. This is kind of like the standard in many modern systems. It's called TIG's tag geometric predictor. Okay, that's the name of the predictor. So how does it work? So that TIG usually has like multiple predictors, okay, multiple tables. And each table is kind of like, address and hash a little bit different. And each one takes a different history. So that's the main thing in TIG, is not just using one history, but also using different histories, okay? So TIG has these different histories, and then use some hashing function to kind of index these tables. Then within that table, it's basically the same thing as others. It goes and read that particular kind of tag, which is kind of the index of this, and then bring out the prediction, okay? And then it's kind of like ask the prediction for all of these guys, okay? So you ask the prediction for this one, this one, this one, and this one. The idea is that if you see the same kind of history, that same tag here, then we're gonna pick that number. If there is no match between any of them, then we just use our base predictor, whatever it is. Okay, so this is a G share or is it the 2-bit or whatever it is. This one just goes through unless the tag that we are seeing, basically the hash that we are computing, is matching with one of these tables. Okay. And then usually it takes precedence. So like this one, if it's a match, then you get that one. If this one doesn't match and this one takes a match, you take this one, and so on and so forth. So there is different terminologies that we usually use for this. What is going on inside here? This is usually the predictor inside is usually the same old 2-bit or 3-bit predictor. So each line, again, each row in each of these tables is the same predictor. Bimodal predictor. The base predictor could be also a bimodal predictor, or could be like a G-share type predictor. Okay. So why is it called geometric predictor? Because this H's, this histories are based on this series of this L series function, which is a geometric function that is like, the formula. Let me see if I have the formula. Yeah. So this is actual formula. The mathematical formula creates like, geometric series. Okay. So it's like, for example, for alpha is equal to 2 and L1 equal to 2. This is generally the history that we are talking about. Like the first two, the last two branches, the last 4 branches, 8 branches, 16 branches, 32 branches, 64 branches, 128 branches. Okay, so essentially what happens is that any of these kind of 4 tables, 5 tables use a different history. So this one takes 2, this one takes 4, this one takes 8, this one takes 16, for example. Okay, and you can continue this depending on how large your take would be. Okay, question.
I understand the idea of the prediction and the tag, but what is U used for?
Oh, so U is usefulness, because I'm gonna actually get to it. So the idea of U is that these tables gonna get full. Okay. So when, for example, this table gets full, okay, and a new branch comes that I haven't seen it before, what should I do? It's the same idea of as a cache, right? A new data comes, you don't cache it. What should we do? We should kick someone out from this table, right? Which one should we kick out? The one that hasn't been useful recently. So this U is just a counter that counts the number of times we actually use this, and indeed it was a correct prediction. Okay, so we kind of like, keeping track of this U whenever we use this prediction and see if it was useful or not. Yes.
I thought the hash itself was the index, so it would be like the tag. So how does U supersede the tag?
No, U is a counter. So an address comes, let's say a history comes, okay, a new branch comes, all right, and we check the tag, okay. And then let's say the tag matches with this T1, okay? And we pick this one, okay? For let's say this line, okay? So we bring this and then we make a prediction, whatever it is, okay? Now that once we know the outcome of the correct outcome of this branch, okay? We're gonna go back to the same line here and either increment or decrement U based on whether or not we make a correct decision, okay? And then we do the same thing for everything that we find. Everything that was a match in this predictor, we can do the same. Usually, I think do just 2. So essentially, the one that you use and another one that would have been predicted. But there are different ways that you can do this update. So, for example, one thing that I think take does is just check the tag and see whatever match that exists in the system. They're gonna update the U based on that. Okay. So the U basically gets incremented if we see that, oh, this was indeed predicting correct. It's decremented if it's not being used correct.
So this is not related to if there's a hash conflict. If there's a hash conflict, then all that's out the window, you replace it.
Hash conflict. So if there is no hash match, right? So let's say the branch comes and none of these tags matches. So now the idea is that I need to replace it for this table, and so on and so forth, right? What would I do is I find the replacement, like the candidate for being kicked out, and I replace it with this new branch. And then I'll put U to the default value, which is usually 0. Yeah.
What is the tag? What are we comparing? Because if you look at it, both the hashes will give the same result. How are they different hashes?
This hash and this hash. So no. So this hash is just for finding one of these addresses, right? If there is nothing in here, then you just this won't be a match, right? So the one is for the indexing the table, and the other one for bringing out the tag. Any other questions so far? All right, so let me just continue. So as I said, the T0 is the base predictor. And then we have TI components. In this particular case, I have I equal to 0 to I equal to 4. U is usually just a 2-bit counter. So you don't need a very large counter here. And as I said, the pred is also usually just a regular 2-bit counter, or sometimes could be a 3-bit counter. Okay. So essentially, as I said, the history is really changing. So these different tables, the difference between them is the history that they receive. One is using very, very short history. The other one is kind of using a longer history, and so on. The idea is that we don't know exactly which history is useful for us. So we're kind of throwing the different histories to the predictor. That's kind of like the basic idea here. And we are using a geometric series. You can think about like there might be other ways to do this, of course, but this is kind of like the straightforward way of doing this. Okay. There are terminologies that we usually use. We use the provider component is that the table that ultimately is being used. The alternate prediction, or alt prep, is that the prediction that would have been occurred if there was a miss on the provider. So it's kind of like the second option in that table. Okay. So for example, if there are tag hits in 2, 4, and 2, 2, and 4, and tag misses on 1 and 3, then 4 would be the provider because it kind of takes the precedence from right to left, and T2 would have been the alternate predictor because if it didn't use 4, then we would have used 2. Okay. And then, of course, if there is none of them are hitting, then the alt pred and the provider component would be the base component, because we always query that there is no tag matching there. Okay. So when do we update the counters? So basically, this useful counter U, we update the provider counter because that's the one that matches, right? We updated that one, and we also update the alt pred if there is the difference. There is a difference between the outcome of the provider and the alt pred. Okay, U will be incremented if the actual outcome was correct. U would be decremented if the outcome was not correct. Okay. Another option is that you just increment but not decrement. That's also possible. And then what we usually do is that we are using some form of an age-based mechanism as well, which means that we decrement all the counters from one table all at the same time after a few cycles. The reason for this is that if it takes enough time, it's no longer temporal localities being used. So it's a good idea that kind of kick them all out at some point in the system. So you don't want a branch to kind of go and sit there and never leave that table for a long time. You want to have a mechanism that is nobody's using that particular branch. Eventually, it will be kicked out by itself, right? So that's kind of the idea of that. So what do we do to replace on a misprediction? since we need to allocate a new branch, right? We will go and find the one that has the u bit equal to 0. If there are a bunch of them, usually start from the top, or we pick at random. There are different ways that you can do that. In Boom, we use these 3 different tables, pretty much the same thing that you saw before. So the first one I think is using 2 bits, and then 4 bits, and then 8 bits, but I need to double check that. But that's typically what we do for tagging Boom. So this is actual implementation of tagging Boom. Okay. Questions about tag? Yeah.
So it says that a useful counter is only updated when the alternate prediction is different, so if they're the same, it won't get updated.
It won't get updated now.
Even if it's a misprediction, it won't get updated.
Even if it's a misprediction, it won't be good. Yeah. So the reason is, so the idea that they had was, if there is a disagreement between the two, then it makes sense to update it. If both of them are wrong or both of them are right, you don't need to do it. Yeah.
I'm still kind of confused as to why we need the view in the first place, because there's this usefulness, but it's not really being, I don't know where that usefulness counter is being used.
It's when we are replacing, right? So when you want, so you have this, let's say, just talk about one of them, right? Let's say you have 4 entries, okay? And then you have a U for them, okay? So this is one tag number 1, tag number 2, tag number 3, and tag number 4, okay? And now let's tag number 5 comes, okay? And I want to put it into this table. Which one of these 4 should I kick out?
Oh, so it's not based off of the hash conflict, then based off the least recent.
Least recent, yes.
Least recent.
Well, I mean, this is like, assume that this is a fully associative cache. Right,
I see. That makes more sense.
Right.
That's where I was having this understanding.
yes.
Is it possible for the U to become less than 0?
Well, this is a 2-bit counter, okay? So you kind of, if you decrement it, it rolls over to 2. But usually you put, like, you never decrement below 0 and you never increment above. So you would kind of, you would limit the amounts that can be go up or go down. Just a simple hardware design that you can put.
This replacement is done across all the histories.
No, usually the one that you picked and it was mispredicted. So that's the one that you do.
Looks like we are doing it in a series, right? So we don't know which one is predicted.
No, you picked one at the end, right? So you picked one of them, one of those 4 at the end. That's the one you pick, as your misprediction.
It could be multiple mispredictions, right?
Multiple, no. So you make it this, so this is how you do. So on a misprediction, okay, not on a miss. So for example, you see that that there is a tag, right? And then you make a tag, and sorry. Yes, on a miss, you pick the each one, and then you see you use the U, and then you update them. Yeah, you're right.
Can you repeat that?
So on the miss, if it's not in any of these tables, right? You need to update the tables, right? Either all of them or the most recent one. In order to do that, then you look at the U.
Okay, yeah, that makes sense.
Yeah.
So it will only update the table on risk prediction. It won't update on just the miss.
It won't update on just a miss, but there's the same thing. It could be the same thing, right?
Like, let's say, like, if it's not in one of the tables, then
your base predictor, if your base predictor is doing fine, then you're good to go. You don't need to add it, right? There's no point of adding it to the table if your base predictor is doing a fine job, right? You only do it if none of your predictor can predict this.
Base predictor is addition.
Base predictor, I think for original tag was just a 2-bit predictor, but nothing prevents you to. I think in Boom you can essentially kind of first query your BTB, and then based on that you use your take.
There's a there's a multi-cycle lag between the view being updated and the next predictions coming in.
Next prediction coming in, yeah.
So that like multi-cycle lag has the potential to be non-correct for those like two branches or
If you have like bunch of branch, and then all of them happens to just exactly map into the same same table, then yeah, you might be lagging behind for sure. But again, this is a prediction, right? It's not a correctness issue. So it's at worst your predictor is just accidentally or non-accidentally make it incorrect or correct decision, because it might be also correct, right? You can get lucky and it might be correct. All right. So yeah, definitely recommend you to look into the tag algorithm and see if you can implement it. There are like tiny bit of details of which one should I pick and all that I think if you read it, you will probably get more out of it. But if you have further questions about like particular implementation, feel free to ask and we can clarify it further. Okay. Since we don't have much time, I want to quickly go over this and not go through the detail, but generally, as I said multiple times last week as well, given that this kind of the problem of branch predictor is really pattern recognition, pattern detection, and some prediction, this kind of screams machine learning, right? Because machine learning is essentially this, features, some function, and some outcome, right? So of course, the machine learning could be potentially very, very helpful in branch predictors. And in fact, many of modern systems do use machine learning. To kind of give you one simple idea of how machine learning could be used, you can use like a old multi-layer perceptron MLP for doing detection, where essentially like, this axis would be your history and the weights would be kind of the importance of each of these histories, right? So like, I don't know, like the fifth branch might be more important than the third branch for whatever reason. So this would be generally your final outcome, right? And then you can train a model with many, like, list of different inputs, and then you can build something like this very easily, okay? Of course, multi-layer perceptron is one way of doing this. You can also think about like CNNs and RNNs and all those other things that could potentially kind of further enhance this, because not necessarily all of them has equal amount of importance and so on and so forth. So there are a whole bunch of works that actually look at these kind of like, how do I build this from a sequence of inputs generally to one outcome, which is like either 0 or 1, right? There is actually algorithms for this. This is based on a particular paper. I'm going to skip this. You can actually see it. Like, how do we actually kind of like, train the bias, train the weights, and then using some form of like, how long should we train this? What is the parameters and so on and so forth. Take a look at this. If you have questions, let me know. I want to save a little bit of time. And then again, if you're interested in more ML and kind of see what is the state of the art, take a look at this paper. It's using convolutional neural networks to do the prediction. It's kind of like, published a few years ago. So it's kind of like the newest in this domain. Okay. The last thing I want to talk about is that, if I have a bunch of different good ideas about the predictors, or maybe I have a take predictor, maybe I have machine learning predictor and all those things, how do I choose between them? Should I kind of choose between them during the offline phase and just put one, or should I put both of them or all of them and then kind of dynamically make a decision? And this is where we usually use what we call a tournament predictor, which essentially the idea is that, for example, let's say we have some form of G-share going on here. Maybe we have some other G-share going on here, or maybe we have another predictor here. Sorry. I have one here, and then I have the other one here. And then here we kind of make a decision of which of these two should I use. I could either use it based on the pattern, or I could use it based on some confidence values, as I said, right? Like, if I see that this left one is consistently doing better than the right one, then it's a good idea to use that. So what I'm showing here is just looking at GHR as general history or as like G-share type. But what you could, so this is the original, what we call tournament predictor. But the general idea is that if I have two different predictors, 1 and 2, I can basically kind of like, have some sort of a multiplexer, and the selector is based on some logic, right? Either the logic could be based on the recent pattern, based on the accuracy of each of these two, and so on, so on, and so forth. So that's another thing that potentially you could consider implementing. That not just having one, having multiple, and then decide which one to use. Okay. Another thing that you could do is that if you have 3, then maybe you can have the majority, right? That could be also another thing that you could do. You can assume that like the 2 of them, the likelihood of 2 of them being right is better than just 1. So you can do that. So these are tricks that you can play in order to see. But of course, they all come with different trade-offs, right? Like if you add more, then there's more power consumption and all those things. But so keep that in mind too. Okay. All right, so going back to the design, where we are at right now is we kind of like finished this part. Last time we also talked about the decode and rename, and this week we want to talk about this rest of this pipeline. Okay, any questions so far about things that we discussed today and last week? Yeah.
So for the machine learning one, are they able to get it to run in like the 2 cycles?
Yeah, because it's just an inference engine, right? So for example, something like a multi-layer perceptron is not that difficult to run if it's not like a very deep, network. You can run it for very fast. Yeah.
How would they use the CNN? CNN is only for negative.
Say it again.
How would they use CNN in this case? Generally, it's for negative.
Why CNN? So again, CNN would be useful if you think about this is that your history is something like this, and then not all part of the history has the same impact. Like, if this part and this part and this part is more important than these other parts, then CNN is a good option, right? Because of this kind of discrepancy. Another thing that you can do is that there are tricks that you can actually make a 2D graph kind of thing, right? So if I kind of plot the history and then different overlap of that, then I have a 2D, and then I can kind of try to extract features this way, right? So that's another thing you could do. Yeah.
So the thing that I see that I'm hesitant to with the NLP
Mm-hmm.
is that you have to do like multiplies or adds, and that's a lot more significant than just XORs that would be doing lookup. Is that
But again, you can design multipliers and adders that can do within one cycle, right? So first of all, that's the main reason that we are shifting from 1 cycle to 4 cycles is primarily this. But again, it's just you can have if you have a very fast multiplier, then you can do this within 1 cycle too if you want to. It's just significantly more power hungry. Yeah. But if it gives you good performance, like if it gives you good accuracy, then many people lose. But yeah, I don't think like branch predictor is using machine learning at the moment in like modern, like commercial off-the-shelf systems, at least not that I know of, but it's always like an option. All right, so just again, another reminder of your computer assignments that is due next week. You can do it in group of 2. The idea is that you take the code that we provided and you're trying to implement a branch predictor. You don't need to worry about the power or storage trade-offs for now. Just think about performance and see how you can get the maximum accuracy out of it. But try to be realistic in terms of your design. So don't do like something that's like obviously impossible to implement. What you need to do is that you just upload your code. Try to just upload everything that you changed. Either is fine. And then don't forget to put your kind of like final MPKI into the scoreboard in the Google Sheet. On the Grayscope, we don't need to check anything, but we will look at the report and how you design it, how you explain your design. And if need be, we can just download your code and run it to double check that everything is fine. Okay. How do you start? So there are all these things that we discussed in the class. I give you pointers. I think that's a good place to start thinking about like how to implement some form of take with different histories, how to combine different histories. Some of you might be interested in implementing machine learning. I would be curious to see that. Some form of tournament or dynamic prediction mechanism that you pick between different predictors could be also a good idea. And there could be also other crazy ideas that you can come up with. So looking forward to reading about that. Okay. Any questions about the projects? I see some people had struggles with kind of running it on Windows and all. So I posted like how you can kind of get rid of that issues. I think the easiest would be just try to get your hands on some Linux or Mac machines and run things there. If you still need if you have problems, let me know. Okay. Any other questions? Okay, let's start the next one then. Okay. All right. So, so far we talked about this portion on the top, right? So we talked about reading the instructions and then doing the branch predictions and then doing the fetching and decoding. We talked a little bit about kind of like from here to here, how do we actually do the renaming? So the rest is kind of like talking about the execution engine, okay? So this is kind of the part that we're going to talk about, and this is usually refers to the execution engine or the back end of the processor. And then as you can see, what happening here is that we have what we call the reorder buffer that kind of like, take care of the reordering the instructions when it's being out of order executed. Then we have the scheduler, which is kind of like the big part of any out of order machine, which is a distributed scheduler for Boom core. Then we have the execution unit. And of course, the register file is also kind of like you can consider part of the scheduler. Then you have tons of execution units, different ALUs, floating point units, CSRs, branch, multipliers, dividers, all those things. And then we have the memory unit, which is kind of like, this is what we call the load store unit. That is kind of like the interface between the processor and the memory system, right? And this is where our queues are and the forwarding happens and all those things that we're going to talk about. Okay, so today we want to kind of cover these, and then hopefully by the end of today or by the end of this lecture, which may not be end of today, we're going to be able to kind of cover all these things up until we talk to a cache system. Okay. And again, to remind you, this is kind of how the pipeline is looking like, right? So we kind of cover up to this point. From this point on, the big difference is that things will start getting out of order executed, right? So we're gonna have this, distributed queues. Then we're gonna have our register read and register files, which in Boom we have two separate register files. We have an integer register file and a floating point register file. Then we have a bunch of all of these execution units. And then we have our kind of load store queues here, and then things will be written back into our registers, and then we move on to the next instructions. That's kind of like what's happening. So we're going to talk about dispatch units. We're going to talk about issue, register read, execute, memory, and write back. These are the stages that we're going to talk about now. Okay. And then also as a reminder of kind of the same thing here, that so far we talked about all these parts here, that the fetch takes 4 cycles and then decode and then a little bit of rename or dispatch. Then we're going to have these queues, and then we're going to talk about the issue and register read and execution and write back. And generally, like, the first version had branch predictor as a separate one. But what we're going to have here is that essentially issue, register read, all the executions, and then write back. Okay. So as I said, dispatching, issuing, execution, write back, and finally retired and commit. Okay. So the big difference, as I said, between the in-order processor and out-of-order processor is that if you think about the in-order processors, you have your fetch, decode, issue, execution, write back. Or like, the terminology that we used there was like execution, memory, write back, right? Pretty much the same thing. But in out-of-order execution, you do your kind of fetch, decode, and issue in order, but the actual execution and write back is happening out of order. So there could be instructions that's kind of younger than the other instructions, but happen to be executed much sooner than the other instructions. And then in order to make things back in order and being able to recover the processor and all those things, we'll have this additional stage called a commit stage or retire stage that's going to happen in order, right? And that's where we're going to use the reorder buffer to kind of do those things. And why this is important, what are the trade-offs? Can someone explain why out-of-order execution is so important?
If there's like some execution task that you need to do that's really big, it might like bog down the processor when there's like a bunch of smaller executions that you could do. So basically not blocking the whole execution unit.
Yeah. So you have a bunch of instructions, I would say. And then if we want to do this in order, right? So if for any reason this instruction could be taking so long, why do you think would take long? Anybody can give me a few examples of why this particular instruction, for example, might take too much time? Memory instructions. Data dependency. So if you have things that cause this instruction to not being executed, but you have a bunch of these other instructions here that are kind of like doing their own thing. They don't need for anybody else. They can just go ahead. So instead of like saying that, okay, we don't do any useful work and we just wait for this particular thing to come out, then we are wasting time, right? The ideal scenario is that if you can always do some useful work in your processor, if I can maximize my utilization, then I have guaranteed IPC equal to N, right? If you remember. So if I can always like provide N instruction every cycles, then we will have IPC equal to N. But if I cannot provide enough instructions, then the N goes down, right? So that's kind of the whole motivation. And what are the trade-offs? So what is the main trade-off between out of order and in order? Anyone?
There's overhead to retire an instruction.
Okay, which means what type of overhead?
You gotta figure out, I guess, or return the structure that the
and then what would that cost? Is it performance? Is it something else?
well, I think area and power.
Area, and power. You want to add something?
Additional hardware would be required.
Yeah, you need additional hardware for the first thing, and additional hardware means more area, more power, harder to implement, more bugs, lower yield, and all those things, right? So more design time. So all those things that comes with additional hardware is where the out of order versus so you don't necessarily want out of order all the time because of the complexity that comes with it. You want out of order when you really need the performance. So it's not like out of order is the one that we always use, because out of order comes with its additional things that we need to be worried about. So it's good to have kind of in order versus out of order. So it's still many systems, simple embedded systems are just in order. Okay. So let's just start talking about these things. And the first thing I want to talk about the dispatching issue. That's kind of a big part of an out of order execution. Okay. So what do we need for dispatch and issue? We need kind of these 4 different main things, and that's kind of like really the bulk of any out of order execution. Of course, you need first of all creating some form of a buffer for all these unexecuted instructions, because and if you remember your fetch, decode, and renaming, kind of doing out of order and doing it in kind of steps of 4, and kind of pumping these things into some form of a buffer. This is usually what we call the reservation station or the issue queue. Then we're gonna have to have a method for what we call wake up and select. Okay. And generally for detection of these dependencies, right? So since we are doing this out of order, we have to be very, very careful of not letting things go inside our execution unit if they are dependent to something else. So we need a mechanism for keeping track of this. And not only just keeping track of it, it's also telling the other, instruction that once their kind of dependencies are resolved, they can go ahead, right? So we need to wake them up and tell them that, yeah, now you're ready to go, right? And then the big question that we always need to have is that if I have a bunch of instructions that are all ready to go, which one should I select? Because most of the time I have many instructions that are ready to go, but I can only issue a few of them. I cannot always like run all of them. So we take 4 each cycle, and then sometimes we might have 5 or 6 different options to run into my system. So now the question is, which of those 4 should I select out of those 5 or 6 or even more, right? So the select, logic, the issue logic is a very, very important part of the system. And generally, as I said, for dependence, we have 2 things, right? We have what we call capturing, which means that, if you're running something in the execution unit, we need to be able to kind of capture the data, the new data, and kind of tell these guys that are waiting that, oh, register 2 results are coming back, and whoever is waiting for register 2 results, now they can update themselves and then they're ready to go, right? So there's this kind of complex mechanism. There are many, many registers that are waiting for some results. Once we execute that, we need a mechanism kind of to bring that back, in other words, capture it, and then tell the other guys, the other instructions to wake up and then continue, okay? So we're gonna talk about these kind of things. And again, reminder that we are now talking about kind of this part of the pipeline, really the part that we take we now rename the instruction, and then we want to move things into these queues. And then from these queues, how do we actually issue them and then let them go? Okay, so you kind of like go there and sit there, and then from there they go to the execution. Okay. A big part of the system is the difference between what is complete and what is a commit or retire. So things, as I said, can be executed out of order, but they cannot be committed out of order, okay? That's why we have this notion of what we call a reorder buffer or ROB, which is essentially for each instruction that we fetch, we reserve a slot in ROB and we put it into the ROB, and then we kind of keep track of the status of this instruction. The instruction can stay in the queue and wait for it to be issued. It can be issued and start being executed. Once it's executed and finished, they can be what we call completed, but they cannot be committed before all the previous instructions before it are committed, right? So the reason that we need a notion of commit versus complete is that things can get completed out of order, but they cannot be committed out of order. The commission has to happen in order. Okay, how do we do that? We use the simple things that we do is this ROB, that think about it as kind of rows for instructions. So instruction number X comes and we put it there, and then we put X plus 1 here and X plus 2 here. The nice thing is that since we are kind of fetching in order, then we can kind of put these things nicely in my ROB, right? And then what I would do is that I have kind of like, I can have a bunch of different kind of, entries in this table. Okay, so for example, I can have what we call a complete, and then I can have what we call retire, and can have many other things in my ROB as well, which I'm going to show actually how it works for Boom. And then what I can do is that for like initially all of them are 0, right? And then at some point, some of them gets completed, maybe this one and this one, right? And now but the question becomes that once things are completed, I can technically retire them, right? I can let them go. But which one should I let go? The way that we're going to do this is that we're going to use a pointer called the head of the ROB. Think about this as like a stack pointer that kind of points to the top, the most recent instruction. The head of the ROB is basically pointing to the oldest instruction, okay? This is the last instruction that has been retired, okay? The point of the head of ROB means that anything that reached to the head of the ROB is now safe to be committed because everything before it is already committed, okay? So if the instruction reached to the head of the ROB, in this case, this X, and is completed, then we are free to let it go. We're going to commit it, Okay. We usually also have what we call a tail of the ROB, which is this like the last instruction that we put, so that we kind of then we can put things at the bottom of the tail, and it kind of like things goes down and down. And then we usually implement this ROB as a circular buffer because essentially things are kind of like going down, 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 and then roll over, and then kind of going down this way and this way, right? So it's usually a circular buffer. Otherwise, you have to kind of shift things up, which is a little more difficult to implement. So we usually implement it as a circular buffer. Okay. So again, the notion of ROB is like this place that you put things and you can kind of keep track of it. They let them go once they reach the head. If, for example, this instruction that is in the middle of the ROB has been completed, we cannot retire it until we make sure that everything above it has been retired. Okay, and that's the main notion. And then when we say retire, what really happens is we say that this becomes transparent. This becomes visible by the architectural state. What is an architectural state? The architectural state is memory and registers. Okay, so the things that we cannot roll back. So once you change your memory, you can never roll back that. Okay, so that's why you only want to update your memory. You only want to update your architectural registers when you're absolutely sure that there is no need to roll back. Okay, that's why you can do any messy thing that you want in the macro architectural states. You can have like your messy register files, you can have your queues, you can have your buffers, you can write them as you wish, you can have branch prediction and speculation, and then have this dirty kind of things. But they are all stay within the micro architecture, which means that your programmers, the rest of the system never knows about what you did there. The only thing that you will see is once you're sure that, okay, this indeed is going to be executed, that's why you make it visible in what we call the architectural state, which means that you make it visible to the register file. You also make it visible to the memory. So you actually issue the actual read and write from the memory when things are in the architectural states. You never do it in the micro architectural state. Yeah.
So this data structure, basically, you have your head and you would basically commit in order, but you issue by searching, looking for the next one that is available.
Yeah, so I'm going to talk about the issue and how the issue would work. But yeah, technically issue could be any of these instructions could be issued. We don't care.
What's the purpose of ROB tail pointer of the ROB?
What's the purpose of, because you know where you can put your next one, right? Otherwise, you have to always search to see where's the new entry should go to. Yeah.
So this, I guess, data structure is only for keeping track which instructions are ready to be executed.
For that, we usually don't use ROB. We use what we call reservation stations. We're gonna get to that. So this is just for keeping track of the status of the instruction. Is it executed, or is it waiting to be executed? Is it completed, or is it committed? That's all. Whether or not, for example, the register, because in order to know whether it's ready to go or not, you need to keep track of the registers and a whole bunch of things. There are, architectures that combine reservation stations and ROBs together, but typically it's not a good thing to have because it's not very scalable. It's very complex to implement. So we usually have two separate queues. And then when you put the instruction, we put it in the ROB and we also put it into the reservation station. Two separate tables. We're gonna get to it. All right. So now that we understand the commit, so essentially, where the ROB happens in, for example, Boom, the moment that you actually kind of start decoding the instruction and know what this instruction is, you also put it into the ROB. So essentially what we call reserve a slot in the ROB, and we put things in the ROB. Then, of course, the question becomes what happens if the ROB is full? If the ROB is full, then you have to stop your front end. Okay, so you have to stall your front end because you have tons of things that you need to execute and you couldn't. So you cannot really fetch new instructions. Very rarely happens, but it could happen if your ROB gets full. Okay, so once we decode, we put things in the ROB, and of course, once it's commit, the command comes from the ROB to this different relevant stages, and we let go of that instruction, and now we have more space to bring things in. To give you an idea, usually we are talking about like 196 256 kind of things like that. This is the size of the ROB in modern systems. So this is the number of instructions that can hold. So plenty large. If you're, for example, talking about a 4 issue, you're talking about, hundreds of cycles that it can actually kind of keep track of things. Now of course, it makes sense. Like there could be memory instruction and all that might take a lot of time to be issued. And then the nice thing about ROB is that once we need to flush things, right? All we need to do is that going through the ROB and kind of invalidate them, right? So we kind of get rid of them very quickly in the ROB. Same way that we did for the rat and the register file and all those things. Okay. So now that we know about this, let's actually talk about the dispatch. This is the part that we take the instruction and we need to put it into this queue. Okay. We call it the scheduling queue or the reservation station. This is the table that the instruction comes and we kind of keep track of which data it needs, whether we read this data, whether it's ready to go or not, and all those things. So everything is happening in that reservation station or the scheduling queue. The big decision that one need to make as a designer in the scheduling queue is that whether I need to have one centralized scheduling queue for all the execution units. For example, I can have ALU, I can have memory, I can have floating point operations, I can have multiply, I can have division, many other things. So different execution units. So the question is, do I need to have a different reservation station for each one separately? Or do I need to, or is it better to have just one big reservation station and then assign things to each of them one by one? What do you think is a better option? Or not the better option? What are the trade-offs between these two options? Anyone? So can I have, so let's say I have different execution units, okay? ALU, memory, floating point and all. I can have one, issue queue for each one, okay? A separate. Or I can have one big one that then issue things to all of them. So essentially it's just one centralized unit or a decentralized unit. What do you think is the difference? Yeah.
Well, if you have the one centralized unit, then you're gonna need something to schedule which instructions go where.
Mm-hmm.
If you have many decentralized units,
Mhm.
then you still need to parse which instruction needs to go into which station. And then you also have a lot of duplicated hardware and it could fill up more easily
Which one could fill up more easily?
with the
dedicated ones.
The
The independent
independent
ones.
ones more easily, and their duplicate hardware.
Yes. Okay.
Common when it's possible that they shoot you with the full,
Uh-huh.
because there is a possibility that one of them, the last instruction that has to be issued, that of execution unit is already full, so that won't get.
That won't get executed. Yeah.
So that way that
Yeah.
common unit may have issues, but
Mhm.
other may be full, but that may not.
Mm-hmm. So if the shared one has better utilization, right? Because it's kind of like, it doesn't skew toward particular instructions. It's just as long as it's big enough that can house lots of instructions. In terms of utilization, you get better utilization in this compared to this, because imagining that all of your instructions are add instructions, right? So then this one gets filled quickly, but then these other ones are empty, right? But what do you think is a good thing about this kind of distributed one? What's the usefulness of this? Yeah.
It might be easier to implement, right?
Mm-hmm. It's much simpler to schedule things this way, because now things are kind of dedicated to each one, and then you can just, for each one, then we can quickly go say which one is ready to go and so on and so forth, versus for this one, you're searching a huge, instruction, like set of things. There are lots of possibilities, lots of search needs to be going on and so forth. So you make things decentralized, distributed, and now independently, each one can work for their own, versus this big one. Now you need to kind of, do everything all at the same time. So in terms of complexity, the distributed one is less complex. Okay. Anything else anyone wants to add?
Aren't there like micro ops or something that this is done for?
Well, I mean, at this point, we know the macro ops, right? We know whether this is an ALU operation, whether this is a memory operation. So we already know that for both cases because we already decoded the instruction.
For the distributed case, it seems like the control path would be easier to implement.
Like how?
Because you don't need to decipher like what instruction you're looking at. With
Yeah.
the one where they're all combined,
Mhm.
you know exactly.
You know exactly what this is. Yes. Yeah. The scheduling is fast.
Oh, okay, is that the same?
Kind of the same, yeah. Yeah. So again, short answer is centralized is better for utilization, probably less hardware at some points, less duplicated hardware, but much harder to organize and much harder to keep track of. Decentralized, the opposite of that. Boom is using decentralized, but many modern systems use centralized, many others use decentralized. So there's no like an obvious benefit of one to the other, but just keep in mind that this is what Boom does. So they have actual issue queue. So actually, if you look at this is exactly what is happening. So you see that they have the floating point issue queue, they have the ALU issue queue, they have memory issue queue, and so on and so forth. So they have dedicated issue queues. Okay. The second question is, when should we read data? Like when you have different registers, we can have two options. The first option is what we call read before issue. That is, when we are putting this into the queue, we read the data from the register file and save it into the queue. Or the other is we just put the instruction and the register that it would need. And then once it's issued, once it's ready to be executed, then we actually read the actual values. Which one? And this is usually we call data capture, and this one we call non-data capture. Which one do you think again better? What is the trade-offs between each one? For the first one, what is the good use cases for this read before issue? Why would you think that this is a good idea?
You can just kind of pass the data along. You don't have to worry about going back and reading it.
Mm-hmm.
In that sense, it's super easy. You just keep
Super easy.
Yeah. The other one, you would once it gets to the, I guess, executions, then you'd have to read the values, which would save you like storing those that data in each stage, but then you'd have to go back and
you have to go back and read it. Yeah, good points. Yeah.
For the other one, you might need the data that's not like executing yet.
So
it's like a read after write data hazard or not.
But I mean, in that case, you can always like put like, question mark or something, and then you capture. That's why you need to capture data, right? So, for example, let's say you want a register that you don't know, the value is not ready yet. So you just put not ready there and wait for the data to be ready. So there's no correctness issue in both. It's just a design element. So you can, in both of them, you can. But I mean, based on what you said, which one do you think is easier to find that dependencies?
First one,
Why?
because you're going to the register to, or well, actually. It's an instruction already.
Mm-hmm.
I don't think the other one is more obviously better.
Okay. Anyone else wants to add something? So I think most of the points has been said. So the read before issue is good because of the simplicity. You just read the register file once at the beginning, and then you kind of pass along the data. The problem with that is that now you need to pass along the data, so lots of storage required, right? Lots of wiring, lots of power. And then sometimes you need to reread the register, so there's kind of possibility of like duplicated data and so on. The read after issue, the good thing about it is that you only read your register file once it's ready to execute it. You don't care about the numbers, you just kind of pass along the tags, right? So you say that, okay, it needs register R1, for example, right? But you never actually read it until you really need to actually execute it. So much simpler in terms of kind of, passing the data along. The big problem here, though, is that your register file design becomes very complex because now you need to kind of keep track of things, update things, read things, and so on and so forth. But the data capturing and all much easier because all you need to know, you don't need to pass any data. You just need to tell everybody that who is ready and who's not. You don't care about the actual data, right?
Is
So
it possible that in the first case we may have a stall?
we may have a stall. In both cases, it's possible to have stalls, right?
Read after issue can be fixed in forwarding level,
Mhm.
but read before issue.
Again, so for example, let's say you are waiting for R1, okay, and R1 you know that it's not ready, okay. So what you would put into your reservation station is that R1 is not ready. So you put, let's say, a question mark, okay, and then what will happen is that you do what we call a data capture. That once R1 becomes ready, you need a mechanism to go and update this element in your table, okay. This is what we call data capture. So you capture the updated value, you put it there. Now this value becomes valid, and now this instruction is ready to go. Okay. In the second option, same thing happens. Here you just, again, you have R1 not ready. Difference is that I don't need to store the actual data here. I just have R1 here. Okay. And again, whenever I see that R1 is ready, I just need one bit that tells ready. Right? I don't need the data. I just need to know that it's ready. Once it's ready, I let it go, and it's going to actually go issued. Once it's being issued, it's going to read the actual value. In both cases, we are worried about raw data hazards. The only difference is that they're being handled differently. Okay. So again, read before issue and read after issue is being used very commonly in modern systems. Boom is using this read after issue. So it's kind of like everything is unified register file. We kind of discussed it last time when we were talking about implicit versus explicit renaming. Usually we pair them up. So when we have implicit, we have this as well. So Boom is using read after issue. So it has one big register file that everything is there. In the issue queues, they just put the names and tags. They don't save the values. Okay. So this is kind of like the summary of things that we said. The unified versus where units. The trade-offs is the area utilization and the selection complexity. The read before issue and write after issues. The trade-offs is the register file design, number of reads that we need, the complexity of the issue, and the easiness or difficulty of waking up and forwarding. So for read after issue, things are much more simpler. But for read before issue, things are a little bit more complicated. Okay. So this is how the reorder buffer looks like in Boom. Okay, so this is what we call this is the ROB in Boom. Main thing in Boom is that ROB is in banks. Okay, the reason that it's in banks is that because the issue width of our processor. If, for example, we have 2 issue processor, then we have 2 banks. If we have 4 issue processor, then we have 4 banks. Usually our fetch rate is higher than our issue rate, which means that we fetch more than we can issue. The reason is the issue is much slower than the fetch. So for example, if you had a 4, fetch rate of 4, the issue rate is usually just 2. So we pump things into the system. So what is happening here? So again, the banks is basically giving us the issue. You had a question? Okay. So as you can see, we have a register called ROB head, and we have a register called ROB tail. We store the PCs. In order to save some space, we only store one PC, and then one PC is across the banks, right? Because you don't need to duplicate the PCs. So PC 2000 is for this row in this bank and this row in this bank. Then within each of these RLBs, we have different columns. We have the valid column, we have the busy column, we have the execution column, we have the operation column, and we have the branch mask column, which basically tells you whether this has been is it being speculated or not. And then the examples that you're seeing here is essentially this is, let's say, for example, we have a dispatch, true instruction being dispatched. In this case, let's say an add word or branch not equal is being dispatched. So essentially, when we are dispatching something, we put it at where the tail is pointing at. So in this case, this one and this one goes into this instruction and this instruction, right? So we dispatch two. The executed instruction are these blue ones. So this is where sorry. These are the ones that we are gonna commit. Okay, so these are the completed instruction that we are ready to commit. As you can see, their busy instructions are not equal to 1, and they are the head of the ROB. So since they are not busy and they're head of the ROB, they're good to go. So we actually kind of like let them go. So this add and this multiply will be, removed from our ROB. And then the important thing about Boom Core is you can commit across the bank. So within one row, you can commit all of them if you can. You cannot commit multiple rows, and this is just an implementation that Boom has. But if you have a very high-end processor, maybe you can even commit multiple rows at the same time. This gives you much more performance in some particular cases. And lastly, if you have a bunch of instructions that are being executed, for example, the Boom Core can support 3 execution units. In this case, let's say the first execution unit has the division. The second execution unit doesn't have anything to do. And the third one has the branch not equal. So then you have this valid bits of 1, 0, 1. And then what happens is that once the execution is completed, then we have to remove this busy bits from this. So they're no longer busy, they are completed, they're ready to be retired in the next cycle if need be. Okay? And then, of course, once things are getting executed, then you put the execution equal to 1. So that's really what we do once we put a new instruction. Okay? To kind of give you a little bit more, this is the way that Boom Core is being implemented. Valid, busy, is it an exception or not? The branch mask are basically telling you which branch is being speculated. The renaming state, the floating point status update, other miscellaneous data that we want to. In this one, I'll just show you a few of them, but just keep in mind that there's a bunch of them as well. And let me see. And then another thing for dispatch in Boom is, as I said, we combine all of them in same bank. In same one PC, multiple banks. This way, one fetch packet can basically just directly go and be, distributed into one row of the ROB and the issue queue. And then, as I said, if the head is not busy, then we can commit, and we commit the entire row. And then what we do is that for putting it into the issue queue, all we need to do is detecting the type of instruction and then put it into one of the queues. Because at this point, we know the micro op, right? So we know what type of instruction this is. Well, all we need to do is that we just know which issue queue this should belong to. So this is where we can park these instructions into those issue queues. Okay. All right. So this is what we call dispatch. So dispatch is essentially these two main questions: that should I read before issue or should I read after issue? And as I said, Boom use read after issue. And the second is, do I need to do centralized as distributed? And we go with distributed in this particular example. Okay. So now that we have things into this issue queues, the second question is, how should I issue them? How should I select between these different instructions? Which one should go into my pipeline? And as I said here, there are two main problems. One is that I need to update the existing instructions in my issue queue and let them be ready. And the second is that now I need to select which one which one I should select. Okay. So as I said, depending on whether we do the read before issue or read after issue, or in other words, data capture and not data capture, my wake up mechanism is slightly different. Okay. So in the left side, you see the data capture one, which I read the register file and put it into my reservation station. So now what I need to do is that my functional units, my execution units, needs to basically tell my reservation stations that these are the new data. They need to kind of forward the data back into the reservation station and updates these entries that exist into the reservation station. Okay. But if I do the non-data capture one, all I need to do is just tell them that, your data is ready. Okay. You don't need to send the actual data. You just forward it or update the register file. Okay. So that's the big difference between data capture and not data capture when you're waking up. Okay. So for example, if you look at two examples of modern systems, in AMD K7, we have this kind of like a mechanism where we send the data and wake up to the register. So this is the data capture scenario. In the non-data capture, like Pentium 4, you wake up at cycle 10 to 12, but you actually send the data at cycles 15 to 16. Okay, and this is actually, by the way, a very deep pipeline processor, as you can see. So the difference between them in real scenarios is like that. Okay. The wake up in Boom looks something like this, that essentially you have a bunch of different kind of data that's coming from the execution unit. And as I said, all we're really passing on is the tags. We don't really do anything other than the tags. A whole bunch of things that is happening here that I recommend you to go and read a little bit about this if you want to. But essentially all we do is like once the kind of the destination register value is coming out and ready, we send it toward this present bit, this ready bit. We just change this ready bit to 1. And this is when we say that, okay, this instruction is now ready to go. And we can do this for almost all of them, right? So we just send this request to this issue select logic, and then basically there are a bunch of instructions here. We make them ready, whichever is relevant. And then the issue logic will select one or a bunch of them that I'm going to explain later. And then going to let this go. So essentially, we're going to select the ones that we think is ready to go. Okay. The main thing about the wake up is generally this is just a combinational logic. So the wire delays and the gate delays is a big thing in the wake up. So if you want to have a very performant processor, what you need to do is having something that's quickly can wake things up. Okay, because wake up and select is actually in the critical path of the processor, so we have to be very careful. So now the question is that there are a whole bunch of things that we can wake up. Okay, which one should I select? Okay, so there are two options, but I want to see if you guys have any options. So let's say I have a bunch of instructions in my queue. And let's say all of them become ready. Which one should I put into my execution window? What are the policy? What policy would you use? Yeah.
The one that's been waiting the longest, or the one that's
waiting longest, so the oldest one. Okay. And what do you need for that? Like, how do you find the oldest?
you would have some sort of like a circular buffer that would take care of a pointer to whatever the oldest.
So you need some form of a pointer that points to the oldest. Okay. Any other suggestions? Yeah.
Do we use instruction order?
Instruction order? Okay. So how does that help? You need to save the PC then, right? Would that be even worse than just recording the last, because you can have just a pointer, right? It's probably smaller than just saving the entire PC. Right?
It would save time with the order buffer, because we want to finish as quickly as possible. So we commit there.
Okay. So you're saying that we should again look into the order and find the oldest and then put the oldest in. Okay. Any other suggestions? Yeah.
try to execute as in order as possible. So
Mhm.
try not to like rearrange the instructions. If you
Okay.
can.
If you can, try not to rearrange. Okay.
So that will make it easier for you when you have to retire.
Okay.
Have a 2 to 3 bit counter that specifies, or not a counter, value that specifies the importance of the micro.
How do you define the importance?
Heuristics.
Okay. So you have some form of like second class citizen kind of thing. Okay.
Yeah.
Trying to have the different instructions possible to make use of all the hardware execution usability.
Okay. But I mean, now we're talking about per execution unit. So all of the instructions within that execution units are pretty much similar. So one of them is add, the other one is XOR, and so on.
Per execution.
Anybody else?
Is this taking into account whatever function unit is available from the other?
Well, I mean, it's per unit, right? So if the unit is available, wants to accept something, the question is which one should I select? If the unit is not even ready, then of course we're not selecting anything. All right, so good. We have good discussions. It seems that most of you are trying to find the oldest, which is good idea, and this makes sense. Of course, we have to try to find the oldest. The problem with the oldest is you need to keep track of the oldest, and that's not a trivial thing to do. Okay, finding what is oldest is not easy. So what we usually do is like two options. One is what we call the unordered issue queue. This is basically jungle. It's like you put things and then you just read them, whichever you want. You may like read something that was old. You may read something that is not old. Essentially, like think about it as a table, and then you put things this way, and then you read it this way. But sometimes, for example, if this is not ready, you're going to read this one, and then this one missed its chance, and then you're going to read this one, and then this one, and so on and so forth. So it's completely unordered. But the nice thing about this is very simple, and the utilization is great because you never care about where to put things. You just find the first place and put it there, right? And the assumption is that if this is fast enough, then I can essentially just things doesn't get too old in this system. Okay. But the obvious problem is instructions that they may stay there forever. Especially if you think about branches, this is horrible because if you have a branch that everything else is speculative based on, and then this branch itself is not getting executed, you just keep doing speculation and speculation. And then all of a sudden, if this branch was mispredicted, all of the things you did after, you have to kind of go back and flush them. So if you want to do like second citizen or like first citizen, maybe branches is like the highest priority. You just let them go because everything else is kind of dependent on them, right? So the other option is what we call age order queue, which all you guys kind of like talked about it. So essentially the idea is we always put things at the bottom and then read at the top, right? And then every cycle we shift things upward, okay? So essentially you think about this kind of queue that we put things inside and then we put things out, from the bottom and read from the top. When we are reading these things, then everything has to shift up, okay? The problem with this is very, very, and by the way, this is what we call collapsing queues, okay? It's collapse on itself. The problem with this is very, very kind of expensive in terms of power because you essentially need to shift everything one cycle up every time we do this, and this is hard. Or otherwise, if you want to have some form of a pointer or the PC or some age, then you also need to keep track of that counter and you need to check that counter. And all those things require time, require power. So it's not trivial to do those things. Okay. And as I said, this is kind of like. And then this is basically means that every single slot is being read and written at every cycle. So again, a massive amount of energy consumption and power consumption. Okay, but most modern processors implement both, including Boom. So Boom has both age-based scheduling and unordered scheduling. Okay. So another interesting question is, when should we wake things up? When should we tell an instruction that's ready, waiting for a register, that your register is ready? Three options I'm going to give you. One is that the younger, so let's say I have something like this, add art x3, x2, x1, then I have sub x5, x4, x3. Okay, so as you can see, there is an obvious dependency. So sub cannot go inside the execution until the value of x3 is known. Okay, so now the question is, when should I wake up sub? When I select add, this is option number 1. When I execute add, option number 2, or when add is committed, option number 3. Who says option number 1 and why?
How many cycles does it take for the add to be completed and selected? It's kind of dependent on the,
Let's say 2 more cycles.
then,
1.
yeah, why not?
So what's the difference between, like, let's say if it takes 5 cycles, what's the problem?
Well, if you have your buffer come in and then it's not completed by the time sub gets to the front, you're sitting there installing.
Okay.
So if you know that like, oh, an ad's gonna take 2 cycles, then
Mhm.
go 2 cycles before and say,
Mhm.
here's my sub.
Okay, good point. Who says 2? Someone else should say 2. Yeah.
Can be
What?
forwarded.
Okay, can be forwarded. So once it's executed, can be forwarded. Anybody wants to say 3? Too late, right? So I mean, we're not in the business of waiting for things to be committed. Like, we're gonna do crazy stuff. Okay, so yeah, so we can either do 1 or 2. Okay, so let's see what happens. So this is what we call slow wake up and fast wake up. Okay, the slow wake up is when we are doing things normally. Okay, which means that once we are getting to the write back stage, once the instruction is actually executed and the value is indeed ready, then we wake up the other one and say, okay, this is your value, go and start execute. Okay, the problem is that this is usually takes 3 cycles between them. Okay, because if you have something like, select, data read, execution, and then write back, we're talking about usually 3 cycles difference. Okay, you can hide these 3 cycles by executing other instructions. So it doesn't mean that you necessarily need to stall the processor for 3 cycles. But if everything is kind of dependent on everything else, then I'm stalling my processor a lot. So that I don't like that. So what I can do instead, I can basically say that things gonna be overlapped anyway. So although that at this point that is selected, the value is not ready, but I can tell the other guy that is ready, you just go and start your process. Sorry. By the time that I execute and I have the value, you are the point that you want to be executed and I can forward it to you. Okay. So I'm kind of overlapping things and doing this thing here that gives us then 0 cycles. So essentially then things are perfectly overlap. And if you remember, this was the same idea with forwarding in our in-order processors, right? If you remember in an in-order processor, we also say that, okay, things go ahead. Whenever it's needed, we're going to give you the data, right? So exact same story here. This is just a different way of waking up things, okay? But what is the problem with the fast? Well, the problem is, what will happen if the data is not ready? Then what should we do? Okay. And what do you think, when would be the scenario that this might happen? Can anyone give us an example that we have something like this, but at this point, the data is not ready? Yeah.
Speculation miss. So if you're doing some sort of like operation and following a branch that you taken, it's not taken.
But then in that case, we flush both of them, so we don't care.
Oh yeah. Okay.
Right. So I mean, if the miss is speculation, then we flush both, then that's not an issue. There's another one.
It's a load instruction.
Load instruction, right? So the load is the problematic one. Why? Because here I'm assuming that the data would be ready, but if it's not in L1 or it's not in L2 or it's not in L3, it might take hundreds of cycles, right? So we said that, yeah, you start, but at this point we said that, you know what, it takes another 100 cycles for your data to be ready. So what should we do then, right? So this is what we call the memory, the issue with the memory, okay? So how do we fix this? We fix this by speculative scheduling, which means that we guess that this might be ready, or we guess that it may not be ready, and based on that we issue things, okay? So essentially the idea is that, you know, the big problem is loads, right? So we know that the loads is the problematic one because of the cache hit miss, or because of the load store forwarding that we're going to talk about then what we can do is saying that, you know what, my cache is doing great. I'm going to speculate that the data will be ready. So you just go ahead and run, okay? Then, of course, by similar to any other speculation, we need to do a mechanism to detect that we made a mistake and fix that. How do we do that? We usually use this method called replaying. So if the data is, if you let the things go and we saw that it's not ready, what all we need to do is that saying that, okay, you know what? Everybody just replay, just redo the things that you were doing, okay? So everything that was being issued going to be reissued, going to be continuously issued until we have the data, okay? So it's the same thing as stalling the processor. So there's a mechanism for doing that. So it just makes my recovery a little bit more complex, but there is no correctness issue. So always we're going to make sure that the data is ready, okay? So speculative is scheduling. What do you think we can, how do we make this speculative scheduling better? What should we do? Should I always say yes? Should I always say no? Should I sometimes say yes, sometimes say no? What should I do as a designer? Let's see if anybody else wants to say anything. Go ahead.
Copy paste your branch predictor.
Copy paste your branch predictor. Okay. But this one is for the load.
Yeah.
So you have a load predictor essentially, right? So you can have a load predictor. Any other suggestions? Say again. Load store queue. Yeah, load store queue helps a little bit. We're gonna actually get to that. Yeah.
If your L1 cache is sufficient, you should be hitting most of the time, so you can just do always hit.
Yes. So there are two ways that you can think about this. Okay. If so, first of all, wait. Let me skip this for now, and then I'm gonna come back to this. Wait. I don't have a slide for it. That's weird. So there are two options. If your load's always, like if you have a great L1 cache, okay, then it means that most of the time I'm doing fine, right? So I can do no prediction at all and always say go, okay? If 99% of the time I have a hit in L1 cache, I don't need to go through this process of prediction and all those things. I just always say go. 1% of the time I make a mistake, I go back and squash, okay? But if this speculation is actually very common, okay, it happens many, many times, then what I need is to have some form of a prediction, okay? This prediction could be static, it could be dynamic. So all those tricks that we talk about branch prediction could essentially be replicated here, right? So I can do the prediction, I can look at the history, I can look at the PC, I can look at all those things and see whether I'm making a correct decision or not making a correct decision, okay? So that's kind of the idea. I had this slide somewhere, I don't know where it is, but essentially, but anyway. So what should we do for squashing? Okay, so let's say we make a mistake. What should we do? As I said, we need to kind of get rid of things that we issued and go back and replay, okay? There we have two options. Then option number one is anything between the issue and execute, we squash them all, okay? The problem with this is that there could be many independent instructions in that window, okay? Not necessarily everything that was in between was relevant to that data. It might be just one instruction, but we are squashing like 4 instructions, okay? So a more complex method is what we call coloring, Okay, so essentially we color the dependent instructions to that load instruction. And when we are squashing, we only squash that color. We don't squash other colors. Okay. And then if you have kind of dependent to dependent instructions, they inherit their color from the parents. Okay. So if you have a bunch of them, then they inherit. Then of course the bigger problem would be what would happen if there are two ones that like one from one load and the other from the other load, what will happen then? Then of course, again, it inherits both of them, okay? We usually use this one hot bit, vectors that then easily we can then kind of add this one bits to the next instruction and then let that one bit go and go, okay? So we usually use this coloring in order to squash the color. So essentially on a load miss, this should be on a load miss, the load will broadcast its color, say color blue was a miss. Everybody who was blue that will be squashed. Everything else remains in the pipeline. Okay. So this is kind of like, again, we are at this stage here. Let me see. Okay. Okay, so let me finish this last part. This is very weird that I don't have those slides because I remember I put it. But anyway, all right. So this is the story of issue. Okay, so the issue just go and we wake up and we put, and then the issue selection could be either age-based or just a simple unordered queue. Okay, and then once we issue, now we need to execute. And remember, we do read after issue, which means that once we select this instruction, now it's the time to actually go and read it from the register file. Okay, you could have done read before issue. In that case, the issue then just simply can go forward. You don't need this. But in our boom core and many other cores, we do read after issue. Okay. So how does the read after issue work? So this would be your issue select. Then we issue two instructions. Your register file needs to have limited amount of ports. You cannot like read infinite. So for example, boom core use 5 read 3 writes ports. So you can you can read 5 things at the same time, and you can write 3 things at the same time. Okay. The reason that we use 5 is because many of the instructions only have 1 operand, so you don't need to have 6. You could have had 6 or 8 and so on. But keep in mind that ports are very, very expensive. Okay. And then since we are doing register files, we also need to have the forwarding or the bypass network, because if you remember our register file things are old here, you might have the data that comes. So essentially whatever you read should be forwarded, right? So you need to be updated because we do wake up and issue in the same, like in one cycle after another. So the forwarding is kind of the same forwarding that we had in a regular in-order processor. There are a bunch of muxes, and the data from register file comes, and the mux is there, and essentially it's kind of like, register file data, the muxes, this is coming from the bypass network, and there's a select logic that selects whether you want to do the bypass or whether we want to read it from the actual register file. Okay. Then what happens afterwards? What happens afterwards is that then we feed it into the execution unit. Okay. Execution units, there are multiple things happening in execution units. For example, you can have integer multiply, you can have floating point unit, you can have ALUs, you can have divisions, you can have load store units and all those things. Okay. So many different execution units you have. Usually we pipeline an execution unit in order to make things, doesn't make the clock, slower. So we pipeline. So for example, multiply usually takes 3 cycles, but your regular add might take 1 cycle. Okay. One main thing is for optimization is that in order to make our scheduling a little bit easier, we pipeline the ALU even though that it takes 1 cycle, we assume that it takes 3 cycles. The reason for this is we are now assuming that everything takes 3 cycles, much easier for us to schedule. But in order to optimize, the bypassing actually do happen in the same cycle. So we don't wait until cycle 3 to bypass. We do bypass at every cycle that we want. So we can bypass here, we can bypass here, or we can bypass here. It makes our bypassing logic much more efficient. Okay. but our scheduling is this way. Once we have the data, then we have to, of course, write back. We can do 3 writes at the same time. This is just the way that we designed this register file. You could design another register file that has 10 writes at the same time, but keep in mind that there is a trade-off between power and performance. Okay. Then functional units, as I said, this is just a generic functional unit. A functional unit has some operations that are pipeline, and usually you have some speculative pipeline that you can flush things out, and you can bypass things off of it as well. And then this is just a generic functional unit in Boom Core that if you, for example, instantiate one of them, that's what you get. The concrete examples are these functional units that you can see here. Okay. So these are things that I said that to make scheduling easy, the alias pipeline, the bypassing can although happens in any stage. There are 2 register files, one for floating point operations, one for integer operations. If your processor only support integer operations, then you will have only integer register file. Most of the most of the modern processors have both floating point and integer. Okay. And then another thing that you can do is that what will happen if you need to read more registers, then you arbitrate, right? So you say that, okay, if I have only, let's say, 4 ports, and if I have like 3 instructions, all of them needs to read 2 things, then you have to kind of like add 1 more cycles for the issue, right? So you say these 2 reads first, then these 4 reads, right? So, or generally any arbitrary. So there generally you can have this trade-off between power and performance if you want to have less read ports. Okay. All right. So let's stop here. Then we're going to talk about load slower, and I'll try to see if we can find that slides I've been missing as well. Any questions? Cool. All right. So see you guys on Wednesday.